I will.
Yeah, tell me just when I should go also to the
Yeah.
slide show.
Okay, we are live. We are live. Okay, so we are live. Hello world again. While we are waiting previous session to finish in 1 minute probably. Again, I want to remind you to try the networking opportunities with fellows like you. There is Q&A but tab here in the chat window. You can either chat in the general chat of this presentation or in the Q&A to ask some questions. My colleague Ilian, who is probably finishing the previous session, will join us in a minute. And here with me is Dr. Martin Romacker. Martin, are you a doctor actually?
Yes, I am.
That's good. Okay, so that's satisfying. Working for this industry is good to be at least doctor. Okay,
Yeah.
so also you can visit our exhibitors booths, and there are very interesting materials from our partners. So you probably will find some interesting information. You can make new connections with our partners network. So this is our aim to present our partnership network. Here's Ilian. Ilian, I just said the important stuff in the just before the session. So I leave the floor to you to present Dr. Martin Romacker. Martin, good luck.
Thanks a lot.
Hi, Martin.
Yeah.
Thanks for being with us. Hi, everyone. Just a quick intro about Martin and his talk, and I'll hand it over to him. We're lucky to have Martin Romacker with us. Martin is maybe among the fair data pioneers. We've been meeting on conferences, for many years. So I'm finally glad that we actually have better communication now through our direct projects that we are working on at Roche. Now to the point of his talk. Of course, Martin's role is a data and information architect in the scientific solutions engineering applications at Roche. Martin is interested in various topics from scientific data curation, text mining, semantic search, and terminology management. And he will be sharing with us today Roche experience on building federated fair data knowledge graphs, leveraging their scientific interoperability hub. My personal interest to you, actually, in the question, I would really like to see, or at least to understand a bit more about those 80 productive applications that are already hooked in and consuming high quality, semantically, normalized data from this hub. Over to you, Martin. The floor is yours.
Thanks very much for the introduction. So I'm just starting to share my screen, and I will bring up the slides. Switch to the presentation mode, and last but not least, switch on the laser pointer. Yeah, so I'm going to take you through a journey that really shows the maturity of semantic technologies and knowledge graphs that we have reached these days in the pharma industry. I kick it off a little bit high level from the industry perspective, and then I go into various achievements that we have made at Roche and finally show to you how these federated knowledge graphs work in action. So looking into our industry, and these are slides which are already 3 or 4 years old, it was in particular the executive people from larger pharma companies that kicked off the idea of changing our industry into a data-driven industry. Vas, for example, from Novartis, he said he wants to reimagine Novartis as a company of medicines and data science. And also the company that I belong to, Roche, we have quite some strong statements of our executives, like our chairman, Christoph Francis, when he was asked whether Roche should be more a company like Google, a data-driven company, he said, "Oh, absolutely yes." And also our CEO, he says that the innovation is happening outside of our company. So how do we get external data in? How do we align it? How do we materialize it? And I just spotted also one interesting fact already a while ago is where an AI company acquired drug candidates from Janssen, the pharma company. So I think the belief formerly was that these companies would work for us, but I think now with all these new technologies around And the data, I think they're entirely new business models. And indeed, I think the insights business, the data business is going to be an important pillar in the pharma industry. So we're also talking here about the fourth industrial revolution. I think you might be familiar with all of these different words which are floating around in our realm. Bringing these together, and this is what you see on the next slide, which I have taken from my colleague Rick van Bruggen from Neo4j, looking into the digital transformation and the megatrends that we see, like data-driven discovery. In our case, it's data-driven drug discovery, hyper-personalization. I think for us, it's personalized medicine, enhanced decision-making, massive data integration, where you really have integrated views, bringing together a lot of data. And last but not least, also AI and machine learning. All of these megatrends at the core rely on connected data. And this connected data, on the one hand, is supposed to be fair. So the acronym stands for findable, accessible, interoperable, and reusable, which has also become a common theme in the industry to drive our data management strategy. But of course, you should not forget about data quality. This is why we talk about fair plus Q data. And in order to achieve this connected data at the center, you need to work on data standards, and this applies to terminologies, metadata, dataset models, and ontologies. And this is exactly what I'm going also to explain throughout this talk. Looking now a little bit more into the Roche Genentech landscape, we have done a big transformation from application-centric to information-centric. And this is also then based again on the fair data principles. I have a very nice definition here from a colleague of mine, Olivier Roche. When you think it from a human perspective, fair data means the ability for a scientist or a data consumer to find, access, and understand the data without the presence of the data owner. So the data are self-contained, well-organized, harmonized, semantically meaningful, and you don't need to go back to someone to really understand what is in your data. More importantly, in our transformation journey, I think is the second part for machines, that it is the ability for a machine to automatically find and use the data. So really make data machine actionable. And 5 years ago, or 4.5 years ago, Roche Genentech, we started a global program, which was called EDIS, standing for Enhanced Data and Insight Sharing. And during this program, we were entirely flipping the coin. And the blueprint for this, which is an abstract model, are called the Roche Data Commons. So in essence, we have 5 different layers, starting with the infrastructure. This is where your data physically resides. Then in layer 2, you have your scientific data assets. So this is really the data management, where you describe the metadata of your data, you manage the access to your data assets, and you also have workflow languages to make data transformations. But the most important point here comes at layer 3, which we call the harmonized data access points. And this provides an abstraction of key data from layer 2, and you want to facilitate it for search and for data access. And these harmonized data access points entirely move away from applications. They're really organized around data or information types, like, for example, adverse events, clinical studies, digital biomarkers, disposition expression, flow cytometry, also patient sample study, you name it. But that's really flipping the coin. So we don't look into applications that contain data. We're really putting data at the heart of the organization of our data management. Then at layer 4, we build integrated data sets out of layer 3 and 2. And at layer 5, we have the analytics and the visualization. So we eventually build applications on top of our data, because you may imagine applications go, data stays. So this is a kind of a driver of our new approach. And the important layer, which is a vertical bar here that holds everything together, are the reference data services. And this is where the terminologies, the metadata, the dataset models, and the ontologies are defined. And now looking into the verification process, I think this is also something that you need to understand if you really think fair. Everything that you have in your universe, in your data ecosystem, is a resource. So a data asset sitting on a physical file server is a resource. A metadata element that you attribute to this is a resource. Any kind of elements that you have are resources. And verification, so really making your data fair, in our world happens at layer 2 and 3. This is where we bring in the URIs, or the global unique persistent resolvable identifiers, and harmonize the data. And at layer 4 and 5, we only read the data And if we still have any effort to do data transformations going from layer 3 to 4, then we have failed on verification. And we have very, very nice evidence already in our organization that you can really natively go from layer 3 to 4 without running any transformation or integration pipelines. So now looking into verification at scale, and looking into key capabilities, just would like to mention that this week, by the way, we have published a FAIR playbook for IT professionals, as we are aiming at an open public-private infrastructure of FAIR applications, services, and data. And we really see this as an industry topic, but we also see this as a topic that's related to our commercial content providers, academia, research institutes. And this playbook has been written for IT architects, business analysts, and software engineers. And what we're aiming at is FAIR by design. So our understanding is that IT is a key enabler. So the IT organization has to build this infrastructure so that we have FAIR application services and data. And at the end of the day, why should the people who generate data, or why should the people who acquire data, why should they care about FAIR? I think the key people who are charged with this transformation are the IT people like ours. But in contrast to this responsibility, so far there's still a rather shallow understanding what FAIR really means. And in order to bring this closer, we also looked into, defining this a little bit with, these are homegrown definitions around what a digital object is and how this then relates to FAIR. And our first definition is that a digital object is any kind of data that exists in a digital modality. It can either be a representation of a physical object or a process. And then there are two different kinds. So there are first-class digital objects that are born in a digital modality. And these are, for example, things like if you take an MRI, where you make a picture of a patient, and this directly goes into a digital asset. On the other hand, there are some objects that will never be digital or never be born digital, because they're physical objects. Think about, in our case, in our industry, about a sample, a specimen in a fridge, or a specific drug, a drug batch. This is a physical object. And now what you're doing in our world to represent this, you're creating a digital object as a digital twin that represents this non-digital object. And typically you do this in a registration system. So you register a compound, you register a batch, you register a biospecimen or an aliquot of a biospecimen. And here comes, I think, one of the fundamental misunderstandings that are possibly still around. Born digital does not necessarily mean born fair. And this is something I'm going to cover later on, looking into the FAIR maturity indicators. I can have, for example, a PDF document sitting on my hard drive, and I give it a path C : / my document / name / document name. This is a digital representation of it, but the representation is not fair. Why? For example, because this representation doesn't have a global unique identifier. So what we need to internalize as a message is that FAIR is above all about the how and not only about the that. The fact that I can find something does not necessarily imply that it is also fair. FAIR is how do I find something? And here again, it's always about the reference of this digital object. You can get some more information about this if you go to a page from the Pistoia Alliance. This is a non-for-profit collaboration in the pharma life science industry, where we've built a FAIR toolkit. The link will be in the presentation, and the presentation can be shared. And this is, for example, where you see some of the FAIR maturity indicators, the so-called FAIR metrics. And here, as you see, for example, for findability, it explicitly states that data and metadata, there's a strong emphasis in FAIR on metadata, are assigned a global, unique, universal identifier, which is also persistent. And ideally, you also use what we call community vocabularies to describe those resources. So there's a clear definition what FAIR is and what FAIR means, and how you can also assess the FAIR maturity within your organization. So looking now into verification at scale, and now we're heading towards the capability stack, and I've put here this lengthy text which are from our FAIR playbook. I don't want to highlight everything, but I think there are these three levels. So one is you have terminology management that you typically do in a terminology management system. And I think the representation here is typically canonical. So you have a concept that has a preferred label, it has a textual definitions, you provide a set of synonyms, and you also provide cross-references that link semantically equivalent concepts in other internal and external repositories. And again, every concept is represented by a global, unique, persistent, and resolvable identifier serving as reference. Now going to the next level, it's the dataset model. So a dataset model is a table-like structure that you also want to fully harmonize across applications. And typically the columns, the headers are the metadata elements. People also call them variables, field names, properties, attributes. You typically bring them into a metadata registry where they have the same rich descriptions as concepts. And by adding them to the metadata registry, you also form a metadata dictionary and a metadata catalog. And these elements can then be reused in a fair way to describe your data sets. And for the data sets, you can also then, for example, determine some constraints on specific variables, metadata elements. Like, for example, when you have an age unit, you can say this is the value domain is a terminology where you have year, month, and day. Or you can also say it's a data type, the value domain, and then you can say whether it's string, Boolean, date, and even specify the format. Again, every metadata element has this global, unique, persistent, and resolvable identifier. And also the data set that you describe has this global, unique, persistent identifier. That's, as again, this kind of table-like structure. So the next level is about the conceptual and logical model, domain ontologies, if you wish. So this is also going in line with more modern approaches to data information architecture, also these new data meshes where you try not to build the overarching, comprehensive, everything covering resource. You rather divide your knowledge space into data domains and subdomains. And you build purpose-driven ontologies that cover some of the aspects for a specific use case with classes and properties. But again, the classes and properties are governed and managed from a central place. And these domain ontologies can then be used as a blueprint for building knowledge graphs. Again, every class and property has a global, unique, persistent, resolvable identifier, and also the logical model, the domain ontology itself as well. I'm a little bit insisting on this because we should not forget how we represent everything really in this fair way using a fair approach. So, and this is exactly what we have built in our scientific interoperability hub, where we start with terminologies. We have a metadata registry where we can define metadata models. We also have this ontology space. And then, which is very interesting, when we federate this at the top level and we bring everything together, the models and the data, this creates a unified model without any integration effort, which I'm going to show to you in a couple of minutes. So also looking into how does this relate to data information architecture to create a full fair representation. I've taken a typical layered approach for data information architecture where you have the conceptual model, where you define the concepts and the relationships, the logical model, where you also have structures, how the data are models with the data elements, the groups, the cardinality, the data types, and last but not least, how is this being implemented? So with our stack, we are covering all these different levels, starting with the terminologies, which span the physical implementation, where we provide, for example, the code lists, but also to a certain extent, the dataset modeling, as also metadata elements have synonyms and cross-references. And then we move up to the conceptual modeling with our domain models. So how does this work? So this is now a screenshot of our tool. This is an in-house implementation that we have built on our own, and it sits on a fair semantic stack where we are using GraphDB as the triple store. So everything that you can see here in this user interface is RDF. And I'm also proud to announce that we have now already more than 90 productive applications integrated. So the way how we do this is that on the one hand, on the left side, we have what we call master terminologies. This is a rough organization of terms into logical groupings, like in our world, indication, gene, anatomical locations, cell types, and so on. But the interesting point is that the way how we distribute this across the organization. So we have so-called application space. And you can imagine that an application is a partition in which we manage the terminology resources for an application in our space. But this is customized in a way that an application gets exactly one-to-one what they need. Like you can see, Epics is an application that's a customer relationship management, a global one, where we, for example, have a country list, and they only have the countries that they need with the preferred label that they need. And the same also applies here. For example, this is the trademarks US. You may know that sometimes drugs might have different trademarks in different countries. You can customize this. But everything that is used here is always tied together by this uniform resource identifier. So if I use non-small cell lung cancer across the application space, it will always have the same URI. You also find additional information here, like we have a life cycle here embedded. We have a definition, defined a set of synonyms. You have cross-references, so that means that there are other systems, internal to our organization, that hold also concepts like non-small cell lung cancer. Would be, in our world, things like MESH, SNOMED, MEDRA for regulatory stuff. And then we can calculate the application references dynamically. The next level is about the metadata and the metadata registry. This is where on the left side, we register all the different metadata elements in our data dictionary, again, harmonized with the URI and everything. And here, for example, to describe a demographics domain, where you describe patients or so, you see that we have typical elements like country, or for example, age to describe age units, age to describe the age, ethnicity, and further levels. And these elements are harmonized and then used, for example, in a harmonized data access point to describe a subject in the demographics domain with this variable. And again, this variable, if I use it elsewhere, will always have the same URI across all the different table-like structures that we're having. And then I can also specify further information here describing the properties of the usage of this variable, which is completely contextual, where I see the application terminology. It's the value domain, sorry. It's an application terminology. In this case, we are supposed, that's imposed by the standard, by the regulatory standard, to use the 3-letter ISO code for the country. And the next level in this stack is really building ontologies. We have built this capability into our tool. We don't want to compete with Protégé or with Top-Rate Composer, but by doing so, we really ensure that these global unique persistent identifiers that we are using across the space are really consistently used. And this really pays back when we try to federate our data, which you will see in the example at the end. So this is a project we're doing with our therapeutic area, which is called Inflammatory Infectious Disease in Ophthalmology. And we built a model for them where you find, if you are from the life sciences, typical concepts like a drug, a tissue, a biomolecule, a cell, a disease. These are the concepts. And then you can also associate here specific properties that, again, possibly also have a domain. I just would like to draw your attention to the last class here, a gene variant disease association. So what you're looking for, in particular in personalization, is to find a pattern where a genetic variant is associated to a specific disease. And this is what is described here in this class. And we also give we give the evidence for this, the p-value, the odds ratio, and so on. And this is now what we can also then export from our system. So we're using Shackle here as a constraint language and create a turtle file out of it. Well, here you have a graphical representation of the ontology that you have seen before. And this is what we mean by purpose-built or purpose-driven ontologies. We don't want to cover everything. But what we make sure is whenever in one of those ontologies someone uses the class drug or the property target molecule, it will have the same URI. So here we see the gene variant, the gene disease variant evidence. On the left side, you see the disease. On the right side, you see the associated gene plus the values. And this is what I will show to you in the next slide, the example. So how do we federate knowledge graphs? So in essence, we're using this capability end-to-end along the entire data management value chain to build domain-specific knowledge graphs. The snippet that you see here on the right box, taken from GraphDB, is about the I2O knowledge graph. And here's just an instance of the data we loaded onto this ontology for a gene disease association evidence. And one part here is that this is about Parkinson's disease. At the same time, we have built a knowledge graph where we bring together the competitor information. So this is about the 100,000 records we acquire from external companies about the competitor space, starting from development until post-marketing. So this gives us a lot of information about what's going on in the market, what our competitors are doing, maturity, indications. And of course, when you are now a scientist and you find an interesting signal, you also possibly in a portfolio decision, you're interested to know, okay, what is the landscape for Parkinson's disease in this context look like? And then you get here in this graph, you get all the drugs which are in this cycle. Then you get also here a specific drug that has a drug type. It's a biological drug. It's also coming from a company. It is has a developmental status. It's in the preclinical phase and additional information. So now, by federating these two graphs, you can really start to ask extremely interesting questions for your portfolio decisions, whether you want to move a specific project forward or not. And because of the fact that in these two graphs, which are completely independent from each other, we use the same global unique persistent identifier for Parkinson's disease, this join here comes with zero integration. You don't have to do anything. So this is what we mean with fair by design, prospective verification, and an end-to-end implementation of a fair data management value chain. So having said this, I'm coming now to my conclusions. So we need high quality, standardized, and linked data. This is the foundation for digitization and insights generation. And a phrase which I really like to repeat frequently is, when you really want to adhere to the FAIR principles, you intrinsically tie your data management to semantic technologies, because this is where the FAIR infrastructure relies on. Data integration based on interoperable domain knowledge graphs is what I've shown. So you can have as many of these graphs, and they would be able to be unified, and you don't have to do any kind of integration. So a fair ecosystem at scale based on knowledge graphs really has become a reality. I also want to repeat that FAIR is about the how. So this is really the cookbook, that you have to follow the guidance from the FAIR principles and not only about the that. We're also looking into new architectural approaches, as I've mentioned with the Roche Data Commons. And here the interoperability of terminologies, metadata, dataset models, and ontologies is key. And as a data management strategy, as an industry, or even as a community, I think there's an urgency to build and integrate semantic capabilities to make this open public-private semantic infrastructure of fair applications, services, and data a reality. And at the end of the day, it's all about semantics. And with this, I'm at the end of my presentation, and I'm open for questions. Thanks a lot.
Thank you, Martin. We have some 4 minutes left for questions. So let me try to quickly sift through the questions. And I also have another one from the social media. So a quick one about this FAIR Playbook. People want to know whether you are going to share the link, or is this a public document? Could it be accessed? So people are really curious about that.
I mean, so far it's not public. We just released it. But as you may know, I'm very much in favor of, say, taking this as a community effort. So I will internally really try to make this public one day. I cannot say when, but that's what I would like to do. But hopefully there will be a way to really get this out.
Okay. A quick question from the social media networks. How easy is to hook up new business applications that could consume, data from this hub?
Yeah, this is, I think, one of the most important questions. It's very fast because we reuse what we have. So when a new application comes on board and we're receiving a list of indications of drug names, of anatomical locations, usually we have already about 70, 80, 90% of those. So I just had a conversation today with a colleague, and whilst we were discussing, I was able to spin off her application. Of course, not complete in the sense of the content, but she could immediately connect with the API. So that's one of the reasons why we can really support so many productive applications whilst being a rather small team. So we are really very agile and fast on this.
Good to hear that, because we have the same experience with other customers. This speed and to add new use cases on the fly and to demonstrate business value, which is much more important than that. A quick question here from the chat. In a knowledge graph, is there a difference between the logical and conceptual models?
Yeah, I think that the logical models are really closer to the physical implementation, where you it's also more table-like, so that you can also, for example, translate into a database table or a kind of a schema that you may want to know, may want to use in a doc store or whatsoever. And the conceptual level, this is really about ontologies. So here we are really talking about classes and properties. And at the logical level, we are more talking about metadata elements and value domains in the sense of 11179 for metadata registries. So there's one difference. Also, maybe if I may want to pick up one question about the country. This was possibly where I was not.
Just
actually,
notice it.
The countries are modeled with URIs. What we do is that we expose the countries as 3-letter character codes. We can also expose them with 2-letter character codes or with a name. The label is just, say, the pretty print stuff. And behind every country usage, whether it's 2-letter, 3-letter, or full name, we always have the same URI. So sorry for not pointing this out. And the other question is about the ontology editor. The reasons why we don't do this is governance, because we have this full management chain from terminologies over metadata into ontologies. And we want to prevent that our knowledge, our URI space proliferates. So if many people work with different tools and they will create new URIs for the same thing, and in our tool we can govern it, but I can export everything into Protégé or so, it's not a problem, but that's then more for visualization. It's a very good point, but this is the reason why we've taken this route.
Thanks, Martin. I think it's good time now to switch to the other talk. Thanks a lot for being with us. I hope that you'll be able to stay for a little longer. People, if you want to get in touch with Martin and ask specific questions, you can find him on the platform, and we'll be waiting for you in the next talk with the Institute of Engineering and Technology. Thanks once
a lot.
again.
Yeah, bye-bye.
Bye-bye.